Hello everyone, this is Professor DePaulo, and today we're going to be talking about basic probability and going over some of these probability concepts and examples of issues occurring in probability here. So we know that basic probability, P, the probability of something occurring, is equal to the number of successes, or whatever you're talking about, whatever you deem a success, over the number of outcomes. This is what's called the empirical approach to probability. There's other approaches to probability, like the Bayesian approach, which constantly updates depending on events that have already occurred, but that's outside of the course, way outside the course, right? So beyond another probability course, where you can talk about Markov chains and things like that. So simply, flipping a coin, a fair coin, you have two outcomes, and I ask for the probability of heads on one flip of a fair coin. Well, there's only one head on a fair coin, and there are two options, heads and tails, so that equals 0.5. So we always write probability to 4 decimal places. That's the standard for writing it out. It's always written as a decimal. You do not leave it as a fraction, right? Probability of getting a 3 on a 6-sided die. Well, there's 6 sides. The number of outcomes is 6. There's only one 3, right? So it's 1 out of 6, which is 0.1667 rounded. Right? So pretty basic stuff here. Number of successes over number of outcomes. However, if we start looking at multiple events, then we throw in the addition rule and the multiplication rule. Let's do one more for basic probability, because I want to talk a little bit about cards again. So the probability of getting a king in one draw. These are all one draws, by the way, right? A king in one draw of a deck of 52 cards. Right, well, we know that there are 4 kings. There's a king of clubs, a king of spades, a king of diamonds, and a king of hearts. And there's 52 cards, which is 1 over 13, which as a decimal is 0.0769. So it's 0.0769 as a decimal. Let's get rid of that. Okay, so the deck of cards is 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. So there are 13 cards for each suit, and there's 4 suits. And those are spades, which is black, clubs, which is black, right? Hearts, which is red, and diamonds, which is red. So there's 52. 13 cards in each suit times 4 suits gives you 52 cards. Half the cards, spades and clubs, are black. Half the cards, hearts and diamonds, are red. If you're not familiar with cards. Some people aren't. So let's go look at some of these more complicated problems now, like the addition rule. So this means the probability of So the addition rule is always or B equals the probability of A plus the probability of B minus the probability of the intersection between A and B. So that's A and B occurring at the same time. The probability of A and B, the intersection, equals 0 when A and B are mutually exclusive events. So the simplest way to look at mutual exclusivity is flipping a fair coin once. So what's the probability of getting heads or tails on one flip of a fair coin? Well, that's simply the probability of heads plus the probability of tails minus the probability of heads intersection tails. Heads and tails occurring at the same time, right? So probability of heads is 0.5. Probability of tails is 0.5. The probability of getting heads and tails at the same time in one flip is 0. So therefore, if this is 0, these are mutually exclusive events. Now this adds up to 1. A probability of 1 means it's guaranteed. So when you flip a fair coin once, you are guaranteed to get either heads or tails. There's no other option. So 1 means guaranteed. If the probability is 0, it means impossible. Right? So the probability of getting heads and tails at the same time in one flip is 0 because you can't physically get heads and tails together on one flip of a fair coin. So since this is 0, it's mutually exclusive. So let's look at another addition problem. What's the probability of getting a 1 or a 3 on one roll of a 6-sided die? Probability of 1 plus probability of 3, right, minus the probability of getting a 1 and a 3 on one roll. So the probability of getting a 1 is 1/6. The probability of getting a 3 is 1/6. The probability of getting a 1 and a 3 on one roll of a 6-sided die is 0. Can't happen. So I get 2 out of 6, which as a decimal, you always want to write these as a decimal at the end. 0.3333. So very basic. Let's do one with cards. It's the probability of getting a king or a spade in one draw from a deck. Remember that when you see or, it's one draw. It's one trial. When you see and, it's going to be multiple trials. But or is one trial. So this is simply the probability of a king plus the probability of getting a spade, which is one of the 4 suits, minus the probability of getting a king and a spade in one draw. So we know the probability of getting a king, so there's 4 kings. So it's 4 out of 52. Probability of getting a spade, there's 13 spades, 1/4 of the deck. But here's the tricky part, the probability of getting a king and a spade. Well, there's one such card, the king of spades. Out of the whole deck, there's only one card that's a king and a spade. It's called the king of spades. So these are not mutually exclusive events because this probability is greater than 0. So these are not mutually exclusive events. So 4 and 13 is 17 minus 1 is 16 over 52. Reduce it to 4 out of 13. .3077. And that's an example where you don't have mutually exclusive events and how that you have the intersection there that you have to subtract. Now let's look at multiplication rule. So this is the probability of A and B. So this is more than one trial because it's AND. So when you see AND, it's multiplication rule. So this is the probability of A times the probability of B, given that A occurred already. Now, with independent events, so if the probability of the two events does not affect each other, then it's going to be probability of A and B equals probability of A times the probability of B. So if A and B have no influence on each other, so if A occurs first, and that does not change the probability of B occurring, we have what's called independent events. However, when we have dependent events, this is not the case. So the probability here of A and B does not equal probability of A times probability of B. Those are dependent events. Because here, if I take A first, then the second trial is influenced by what happened with A, what happened in the first trial. So independent events are generally with replacement. So when you have with replacement, you have independent events. Dependent events are without replacement, where the probability changes. So what's the probability of getting let's use cards again. Ace and ace in two draws with replacement. In that order, of course. Ace first and ace second. So this would be probability of A times probability of A. So with replacement, there's no change in the probability. So the probability of getting an ace is simply, let me get rid of this. Probability of an ace, there's 4 aces in the deck, right? So 1 out of 13. 4 aces and 52 cards is 1 over 13. And ace again. So if I replace this ace, I put it back, it's still going to be 1 over 13. Which is 1 over 169. Because the probability doesn't change because I replaced the ace. So let's do 113 times 113. 0.0059 to 4 decimals. 0.0059. That's a very small probability of getting 2 aces with replacement. Now let's try the same problem without replacement. So these are independent events. Let's do without replacement. It's probability of ace times probability of ace given you took the ace out of the deck, right? So that's a conditional. So it's a conditional probability. So we know that this is 1 out of 13. But if I take 1 ace out here, I have 1 less ace. So how many aces do I have left? Well, I have 3 left. How many cards do I have left if I took this ace out at the beginning? Well, now I no longer have 52 cards. I have 1 less card because I took it out. So I have 51 cards. So these are dependent events because the probabilities are changing. These are conditional probabilities. The second probability here is conditional because you're not replacing it, right? So that alters its initial probability. So this is 3 over 51 times 13. Let me just write that as a decimal instead of as a fraction. It's not going to get me anywhere as a fraction. So 113 times 351. 0.0045. So it actually goes down. So that probability is less because we've taken that ace out of the deck than the previous problem. Now you may see multiple trials where I'm not talking about getting in a particular order. So far I've been doing ace first, ace second in that order. Sometimes I'm not interested in order. I'm just interested in total number of successes, right? Not in a particular order. So, like let's say I flip a coin. What's the probability of getting let's try this problem. So let's say I flip a fair coin multiple times. I want to know what the probability of getting 3 heads and 1 tail in any order. So this is total probability. This is not saying what's the probability of getting heads, 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 tails in that particular order, because I could find that over here, right? By just doing probability of heads times probability of heads times probability of heads times probability of tails. This is the probability of getting 3 heads and 1 tail in 4 trials in any order. Right? In any order. So there's a bunch of ways to do this, but the way that I've been showing you how to do this is create the sample space. You can also use the binomial distribution, which we didn't talk about. You can also use you can use the number of combinations. So this would be 4 trials, 4 choose 3, and find the number of combinations, then find the probability that way, which some of you have been doing on the homework, even though I haven't explicitly talked about that, but you picked it up from another course or you know how to do it already, which is fine. I've been saying draw out the sample space. So what is the sample space here? Well, this is how we draw the sample space. Heads, tails, heads. So this is flip 1. This is flip 2. This is flip 3. A little sloppy with the tail, sorry about that. And then we have flip 4. I'm writing on a slant again, because I tend to do that on the tablet. I tend to do it on the board also. I'm not quite sure why I keep writing with a slant on the board. My worldview is slanted, apparently. So those are my 4 trials, and now you would want to list them out. And obviously this takes more time, but it's more systematic. I ran into this issue here where I can't see what's going on. Let me try to separate this a bit. No. So heads, tails. This is supposed to be. So you want to write this so it's not sloppily constructed here. Heads, tails, heads, tails. Did that one. Heads, tails, tails, heads. Heads, tails, tails, tails. I kind of smushed it. You want to make sure you have space to write it all out. Tails, heads, heads, heads. Tails, heads, heads, tails. Tails, heads. Tails, heads. Tails, heads, tails, tails. And the last four here, tails, tails. Heads, heads. Tails, tails, heads, tails. Tails, 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 heads. And then tails, 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 tails. And we want 3 heads, and so you have 16. So you have 4 flips. Actually, whoops, let me fix that. I don't want to do that. Sorry, you have 2 possibilities, 2 outcomes, heads or tails, and you have 4 flips, so it's 2 to the 4th. Gives you 16 total possibilities here, right? So the total possibilities is number of outcomes raised to the number of trials. So 2 to the 4 is 16. I have 16 here. 3 heads and 1 tails. Let's see. 3 heads and 1 tails. 3 heads and 1 tails. 3 heads and 1 tails. What else do we have? Is that it? 3 heads and 1 tails. 3 heads and 1 tails. 3 heads and 1 tails. And the other 3 heads here. 3 heads and 1 tails. There's 2 heads, 2 heads, 2 heads, 2 heads, 2 heads. So I have 4. 4 out of 16 is 0.2500. So that's the probability. Can you do it another way? Like if I do combinations. So I have, so I want 3 heads. So I have 4 trials. Choose 3 heads. This would be 4 factorial over 3 factorial, 4 minus 3, which is 1 factorial. So it gives me 4 times 3 factorial over 3 factorial times 1, which is 3 factorial. So that would give me 4. And that would give me the probability of heads is half. So there's 4 ways I can do it right here. 1, 2, 3, 4. 4 ways. So this whole formula, I'll show you in a second if you want to use that. Probability of heads is 0.5. Probability of heads is 0.5. Probability of heads is 0.5. Probability of tails is 0.5. Right? So that'd be 4 times these probabilities. 0.25, 125, 625 would be that. And the 4 times that would be 2,500. So that matches what I have here. That's the combination way. So basically you take the number of combinations and then you put what's the probability of getting 3 heads and 1 tails. So this is would be head, 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 tails. So what that's saying is there's 4 ways to get 3 heads and 1 tails. And the probability of getting 3 heads and 1 tails is 0.5, 0.5, 0.5, 0.5. Right? So one way is 0.0625 times 4 gives you 2,500. So these are all different ways, and this formula is combinations of n choose k equals n factorial over k factorial n minus k factorial. Right? I think this is like a little bit more extensive than just mapping it out. Now this works if you have a huge number of trials you're looking at. So if I had a lot more than 4 trials, I would want to do it this way. But for small trials, like mapping it out like this is fine. And I think it's intuitively simpler, which is why I kind of work on this, to draw out the entire sample space this way. But if I had like 50 trials, well then I have to do this, right? And this is just combinations, right? So they're equally, they work the same, right? This gives you the number of combinations, and then you find the probabilities of the individual events. Some of you have done it this way before, so you've been doing it this way, which is fine. Now, if I want to find the probability of something occurring one way, like, for example, what's the probability of getting 6 heads in 6 flips? Oh, a fair coin. Well, I could map this out. It's going to be a big mapping, right? It's going to be 2 to the 6, which is going to be 64. So there's 64 possibilities, right? But just think intuitively like this. There's only going to be one order in which you get 6 heads. There's no other order where you can get 6 heads and 6 flips. The only order of getting 6 heads and 6 flips is heads, 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 right? There's no other way you can get 6 heads other than this. There's only one way. So this problem, I don't have to map out the sample space because I know there's only one order of getting 6 heads and 6 flips. This is the order, right? There's no other way to rearrange this. There's only one route, right? So this becomes basically 0.5 times 0.5 times 0.5 times 0.5 times 0.5 times 0.5, which is 0.5 to the 6th power, right? And when I do that, 0.0156. That is my probability. 6 heads and 6 flips. If you wanted to do combinations, we could do it this way. So this is n, this is k. So it would be 6 factorial. Now 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, right? If you did 6 that's what factorial is. 4 factorial would be 4 times 3 times 2 times 1. So if you're not familiar with factorial, that's what it does. It's just basically you multiply everything by every integer down to 1. So this would be 6 factorial over 6 factorial times 6 minus 6 factorial. And this would be basically 6 factorial over 6 factorial times 0 factorial. Now 0 factorial is 1. So that's 1, which gives me 6 factorial over 6 factorial, which cancel out, right? It gives me 1. So there's only one combination. But that makes sense because there's only one way you can get 6 heads, and this is the one way, right? So there's not even the need to do the combination formula. And there's no way you would want to map it out because you'd have 64. You'd be matching it out to 64, right? So that's basically how you'd solve a problem like that. And there's a lot more to go here. I mean, like you can find there's multinomial distribution, there's binomial distribution. We're not doing any of that in probability. I want to keep it very basic. This was as basic as I think I could keep it. So hopefully that helps you with some of the problems. And if you have any questions, let me know. If not, I'll see you online at another time. Bye for now.